Hey, Mrs. KJ here, going over lesson 8.02 Radioactivity and Half-Life. Changes in the nucleus give off radiation that leaves the atom. You have learned about the structure of the nucleus and the forces holding it together. In many nuclei, an imbalance exists between the forces holding the nucleus together and those that would tear it apart. Now remember, it wants to go apart because the protons are all positive. It stays together because of the attraction of the quarks together and called the strong force, and the residual strong force, which is the attraction of the quarks in one proton to the quarks in another proton or in a neutron. These nuclei are unstable and undergo a spontaneous change where particles and energy are lost. This is called radioactivity. In this lesson, you will learn about types of radioactivity, nuclear changes that accompany radioactive emissions, and radioactive half-life. Goals for this lesson: explain the process of radioactive decay, name the three main types of radiation, alpha, beta, and gamma, compare the changes in the nucleus that result from alpha and gamma decay, contrast the penetration of different types of radiation, define a half-life, given an amount of radioactive substance, calculate how much remains after a certain number of half-lives has passed. Radioactivity is caused by the decay of the nucleus, which occurs when unstable nuclei lose protons and neutrons, and this does occur naturally. So you can get the student guide. What is radioactivity? You probably have heard of radioactivity in the news with regards to nuclear bombs, dirty bombs, and nuclear power plants, or perhaps in science fiction where dangerous radiation harms starship crews, or a radioactive insect bite creates a superhero. Radiation can be harmful, but it can also be harnessed for useful purposes. But what is radioactivity? Radioactivity is the decay of an unstable atomic nucleus followed by the release of radiation. The radiation can take the form of a particle or energy. So what makes a nucleus stable or unstable? The stability or instability of a nucleus is related to the structure of the nucleus and the balance of forces that hold it together versus those that tend to make it fly apart. All right, uranium-238 decays into thorium, which is a different element, by releasing an alpha particle. Beta and gamma are other types of radiation. So our alpha particle here is a helium-4. So it's got the 2 protons and the mass of 4. So 2 protons plus the weight of 2 neutrons equals 4. There is a beta particle and a gamma ray. So let's talk a little bit more about a balance of forces that holds the nucleus together. The nucleus is made of protons, plus 1 charge, and neutrons, 0 charge, both of which are made of fundamental particles called quarks. Quarks attract one another to hold protons and neutrons together via the strong nuclear force. Quarks from one proton also attract quarks from another nucleon with a residual strong force. The strong nuclear force, or simply the strong force, acts over short distances to hold the nucleus together. In contrast, an electromagnetic force tends to repel the protons and tends to make the nucleus fly apart. Neutrons help stabilize the nucleus. In stable atoms, these opposing forces are balanced. However, when there are too many protons relative to the number of neutrons, these forces are out of balance and the nucleus is unstable. So again, protons want to be away from each other. However, there's the attraction of the internal nuclear forces. And then in a stable atom, they are balanced. Unstable nuclei decay to become stable. So in other words, there's a reason they decay. They decay so that they become something else that hopefully is more stable. If you plot the number of neutrons n versus the number of protons z for the various elements, you will see that the ratio n over z ratio equals 1 for elements up to the atomic number of 20. So what is that really saying? Well, that's saying that if you look at elements numbers 1 through 20, then you're going to see a certain pattern. So let's look at some examples. So let's look at lithium. Lithium has an atomic number of 3, and the mass rounds up to be 7. So that tells us that there are 3 what? 3 protons, and 7 minus 3 equals 4, so there's 4 neutrons. Let's look at beryllium. Beryllium has 4 what? Protons. The mass number is 9, so how many neutrons does it have? 9 minus 4 is 5. Sometimes they're even, so if we look at magnesium, Magnesium's number 12, 12 protons. 24 minus 12 means there's also 12 neutrons. So that's the pattern that they're talking about in elements 1 through 20. All right. Above Z equals 20, so above atoms with atomic numbers above 20, there are more neutrons than protons. Within this region is a line of stable nuclei, a band of stability. Elements above the band of stability have too many neutrons, decreasing the strong force and destabilizing the nucleus. Elements below this band of stability have too many protons, increasing the repulsive force and destabilizing the nucleus. All nuclei with an atomic number above 83 are unstable, with some more so than others. An unstable nucleus will spontaneously change. Scientists use the word decay to become a more stable nucleus. It does so by emitting a particle or particles and/or energy, which are collectively called radiation. All right, from the student guide, I kept the beginning paragraph and the goals. We have some keywords and pronunciations, but we're going to start here with the ones that we just read. Radioactivity is the decay of an unstable atomic nucleus. Too many protons, not enough neutrons, for example, followed by the release of radiation. I added the word radiation. Energy or particles released during radioactive decay. What makes a nucleus stable? A strong force, so quarks within a nucleon. Remember, a nucleon is a what? A proton or neutron. What also keeps a nucleus stable is the residual strong force, so quarks attracted to other quarks in nearby nucleons or a nearby neutron or proton. What makes a nucleus unstable? Too many protons versus neutrons or vice versa. And nuclei decay into smaller, different elements that are more stable and give off radiation when doing this. I got to make it its own bullet because that's the result of being unstable. All right, radioactively decaying atoms release particles or energy, in other words, radiation. When an unstable nucleus of an atom decays, it releases energy in the form of moving particles and/or electromagnetic energy. This radiation is of three types. You can have alpha emission. Alpha emission means you have a helium nucleus, 2 protons, 2 neutrons, often released from a large atom. You can have beta emission, which is a high-speed electron or positron, which is an anti-electron, from the nucleus, not from the orbitals. Okay, so if you're thinking, wait a minute, electrons aren't in the nucleus, you are correct. But basically you have this huge crazy mess, and of the craziness, you can get a positron, so an anti-electron, or a high-speed electron, actually from the nucleus. And there's also gamma emissions, which is electromagnetic wave. These types of radiation have different amounts of energy and are capable of penetrating materials in different ways. For example, alpha particles can be stopped by paper or skin, beta particles by aluminum foil or plexiglass, and gamma emissions by concrete or lead. Some types of decay also yield positrons, positively charged electrons, or neutrons. Okay, so the big deal with this is, think of an x-ray. Okay, when you go to the dentist or the doctor, they put a lead vest over your chest and they take the x-rays. Well, the x-rays show the bones. Now, it can obviously go through your skin, through your muscles, until it gets to the bone. So that's a way to think about this. It's saying that the helium nucleus, paper is going to stop it. Aluminum foil's going to stop the beta, but it can go through the paper. The gamma is the strongest. It goes through the paper, through the aluminum foil. However, lead or concrete will be able to stop it. So I added the 3 types of radiation. I just copy-pasted it. Again, feel free to add more to your own notes or less, whatever you feel would be the most helpful for you. And I also added the picture because I just think this is a great visual about how much stronger gamma is than alpha, and it also reminds you of what will stop them and what they are still able to go through. Radioactive decay changes the nucleus and forms new isotopes. Large unstable nuclei, or in other words, atomic number, or Z, greater than 83, tend to decay by alpha emission. The atomic number decreases by 2 and atomic mass decreases by 4. Now, that will make sense if you think about what alpha emission is. Alpha emission means that you lost a helium nucleus. In other words, you lost 2 protons 4 neutrons. Okay, so the atomic number goes down by 2 because I lost 2 protons. The mass goes down by 4 because 2 protons plus 2 neutrons equals a total of 4 AMUs, or 4 atomic mass units. So in the picture, we have 92-238 uranium. In other words, uranium is element number 92, 92 protons, and the mass is 238. It breaks down into thorium. So instead of the atomic number being 92, now it's 90. Instead of the mass number being 238, now it's 234. And then also it spits out that helium nucleus. Because it's just the nucleus, there's no electrons, it has a +2 charge. In high N/Z nuclei, neutrons decay into a proton with the release of a beta particle. That's beta emissions. The atomic number increases by 1, but mass remains the same. All right, so in this example, we have carbon 6, 14. So carbon is, atomic number is 6, it has 6 protons, and the mass number is 14. So it spits out your beta emission, okay? And here's the big thing. It takes a neutron, and the neutron changes into a proton. So now, instead of my atomic number being 6, it's 7, because I took a neutron and made it into a proton. So my atomic number goes up. Now, the mass stays the same, because carbon has 6 protons and 8 neutrons. Nitrogen has 7 of each. Okay, so if you need to hit pause and listen to that part again, go ahead. The first time you go through this lesson especially, it's a little overwhelming. In nuclei with many protons, so a low N/Z, protons can decay into neutrons and positrons. These are also called anti-electrons. The atomic number decreases by 1, but the mass number remains the same. Okay, so I took a proton. I took my proton, I had 8 of them in oxygen. I changed it into a neutron, so I have 1 less proton, so my atomic number goes down. However, the mass is the same, because each proton and each neutron weighs 1. So before I had 8 and 7, and now I have 7 and 8. Okay, so in other words, I had 8 protons, 7 neutrons. Now I have 7 protons, 8 neutrons. And of course, a positron. Alternatively, low N/Z nuclei can capture an electron from the electron cloud. So you can have an electron capture. So we look at rubidium, 3781 plus that electron is going to yield 3681 krypton. Okay, so what happened here? Well, I went from 37 to 36. So I got rid of a proton. Oh, but my mass number stayed the same. So I didn't really get rid of a proton. I changed that proton into a neutron. All right, so again, we have this graph, and it says, okay, if you have a good ratio, you have a ratio of about 1 to 1, you're fine. You're not going to have radioactive decay. However, if you have too many of one or too many of the other, then you're going to have the decaying issues. And then that talks you through, well, decays as neutrons and positrons, or decays as protons and beta particles. The type of radiation that leaves an unstable nucleus depends on the ratio of protons to neutrons. So again, if you have too many protons, the protons are going to change into neutrons. Okay, if you have too many neutrons, then some of the neutrons are going to change or decay into protons. Okay, so I copy-pasted that slide into my notes, and I just numbered it 1, 2, 3, 4 for paragraphs. Then I made a table, and I have the paragraph number. I want you to write in what's the issue that they talk about. In other words, why is it going through radioactive decay? What does it lose? What happens to the atomic number? What happens to the mass number? Please hit pause. See if you can fill this out on your own. All right, here are the answers. Atomic number greater than 3. You have your alpha particle. Atomic number goes down by 2, and mass number goes down by 4. Too many neutrons. Neutron becomes a proton. Atomic number up. Mass number stays the same. Too many protons. Protons become a neutron and positron, or it grabs an electron to do this, decreases by 1, and mass number stays the same. Let me know if you need